Okay, welcome everybody to this keynote presentation, this afternoon keynote presentation. This is the fourth keynote of the conference of the International Micro Air Vehicle Conference. And I'm very excited to introduce our keynote presenter, Brandon Gilles. I will read his biography. Brandon is driven by the singular belief that the biggest impact he can have on the world is fostering innovation, and the understanding that a five-fold increase in productivity is the difference between the Middle Ages and now. And the driver of that productivity increase and the tremendous increase in the quality of life we all have is innovation. And for innovation to happen, simplification needs to happen first, so that powerful things can be used easily and readily. And then combined with other powerful things, of course, combined with other powerful things. So Brandon's mission is to make embedding performant spatial AI and CV, computer vision into products quite simple. To enable and foster a wave of innovation powered by being able to embed human-like perception into products across all sorts of industries. I have to say that Brandon is the CEO of Luxonis, a company that is offering very nice products in terms of sensing and novel cameras or novel sensing cameras. I'm pretty sure he will do a better job in describing what his company is offering. But I have to take the opportunity to also say thank you to Brandon, because on behalf of his company, he offered us a sponsorship for our awards, the awards that we are going to present tomorrow in the awards ceremony. So please, Brandon, you have the stage, and go ahead. Thank you.
Well, thank you for that great introduction. So, the thing that I want to cover today is spatial AI in embedded systems. So to give you a background on all those things. So the spatial aspect is depth sensing, using two cameras, just like our eyes, to get depth maps of the world. And then the AI part is, mimicking the intelligence or the, more specifically, the perception that humans have. So this is computer vision, artificial intelligence, which is knowing what things are, what's in a scene, where they are, where they stop and where they end. And so both of these kind of started in the 1980s. So if you look at, spatial perception, this started in the 80s with PhD work, theorizing what's possible of being able to get depth information out of multi-camera arrays and like $100,000 plus or $1 million plus pieces of hardware that took tremendous amounts of power and still didn't really run real time. And AI started in the 80s too, with Geoffrey Hinton theorizing with backpropagation that you could get a computer to learn. And if you did that, then you could have computers solve problems that humans couldn't. And so if you fast forward to, let's say, 2012, we kind of had the first time that AI could really do that, where backpropagation was used at scale to outperform or to match human capability to recognize objects, to do image classification. And if you fast forward again to about 2012, you see depth perception start to be commonplace with companies like Occipital, for example, which started to push the boundaries where they got depth perception into the hands of consumers at, let's say, $500. I don't remember exactly what the price was. And in these systems, that was the first time they were kind of readily available to the masses. And so with AI itself, you saw all these huge applications take off. But they were very, in 2012 era, they were like infinite compute applications. So like Google scale compute and these startups that were, using millions of watts of power to do artificial intelligence. And then with depth perception, that was finally starting to get to the point where consumers could use it, $500. And since then, we've seen this kind of slow trajectory over those years into like more edge, right? And slow being a relative term, right? Like about a decade. But there's quite remarkable when you look at like the course of human history of what we're accomplishing here. And maybe starting in 2017, that's where you saw AI kind of get to the edge, right? So the edge being like a couple MacBooks, something like that. And then you started to see combinations of this where you do object detection, machine learning based object detection, YOLO, for example, with depth sensors, say like Occipitals depth sensor. And then you could make robotic systems that could interact with the world, but you're still talking about compute payloads that are the size of a couple MacBook Pros, right? And in 2017, it was remarkable to see, a laptop. That was like the big deal. Like a laptop can run a real-time object detector, a machine learning-based object detector, and then you could fuse that with depth data. And now you have a robot on that scale, that's taking maybe 50 or 100 watts or something when it's running, that could start to perceive the world like a person can. And you fast forward to now, and Intel's at the forefront of this, and we're using their Movidius chipset. We're getting to the point where you can actually have embedded systems do this. So, we started with, companies that had hundreds of millions of dollars of computers. Those are the only ones, say in 2012, that can harness AI. 2017, you're talking about like a couple MacBooks. And then now we're getting to the point where you can have some tiny thing doing that capability. So having depth perception, having artificial intelligence and computer vision all combined together. And that's where we are now. So that's the brief history in preparation for like the confluence of things that we ran into. Start with the why of everything we're doing. Spatial AI is crazy powerful because you're mimicking human-like perception. You have depth perception, just like our two eyes. You have AI to know what things are, and the fusion of those gives you that capability to perceive like a human on a small device if you can embed it. But there was no way for that to be tiny and light. And the problem we were trying to solve, so this is me trying to solve it with a bunch of my friends got run over, which was unfortunate, by distracted drivers. And so I was trying to see, okay, well, could you build a thing using depth perception and AI that knows when something's on your trajectory? And I was not wanting to repeat the situation where the Volvo CEO is detecting he hit a pedestrian detection system on a Volvo. I didn't want to get run over by my own system malfunctioning, so I sprinted at cars as well. And so this is the first thing that showed me the power of spatial AI. So I was using depth perception and AI together, all kludged multiple sensors. So I was using a depth camera, I was using an AI processor, using a computer, using a bunch of hardware to tie it together and CV functions and everything. To mimic human-like a vision. So, what are you looking at? Where is it? That's now possible, right? And that's what I was able to prototype really quickly, but it was big and heavy and took a lot of power, and it was expensive, and it was not embeddable. And so the problem I was trying to solve, first off, I wanted to know, could you just solve it at all with modern technology, like the state of AI and depth sensing and stuff? And the answer was like, for sure you could. It only actually, once I finished zip tying all that stuff, like writing the code actually only took like half an hour because it was you run the object detector, which car was already a trained model. You have the depth information, in this case was from a RealSense camera. You fuse it together to get the 3D position, and then you get the relative trajectory, and you can tell if something's on your trajectory. But the problem was it wasn't embeddable, and I was wanting to make a bike light that could just tell you if cars on your trajectory for bike commuting. All the folks in my network who were hit were riding their bikes to or from work. And so, every day they'd have 500 cars safely pass them for decades. And it's just that one car that's on your trajectory. You want to know when that's the case. And this proved you could do that with all these advances since, the 80s, coming to being able to do it on edge. And this was prototyped this in 2018, I think. And so, this is somewhere between that laptop thing I said in 2017 to now this is like a Raspberry Pi with a bunch of other junk. But it's not embeddable. You can't really build a product around this. And so we set off to see, well, could you make an actual embeddable version? Does that exist? And the answer is yes. The Myriad X from Intel was the first thing in the world that allowed you to have all this stuff on an embedded system. And so you can see a US quarter there for reference at the bottom, and I'll hold it up to give scale. Hopefully my video is not too tiny. but things are really small. And so the Myriad X was this really interesting chip, but given that it was so new and so bleeding edge, there was no way for just anyone, an engineer, to go develop something. So we found ourselves in this really interesting space that as engineers we'd never been there before, which is when you go to solve a problem, like usually you'd quickly discover oh, that's a problem people solve. And you just buy a development kit and you go solve it, right? And you go make it work in your application. Or you're well, that's against physics, or maybe that will be possible in 20 years or 40 years, kind of like the folks who were initially researching this in the 1980s for AI. It caused an AI winter because they were well, theoretically that's possible, but it requires more computation and more time. With the computers in the 1980s, the reason there was an AI winter is they said that will take more than all of the rest of human history to train a single neural network, right? Based on 1980s computation. And we were in this weird state where it was neither of those, right? It wasn't this is completely unsolvable, or this is by a dev kit. We're this is solvable, but there's no dev kit, and the chip exists. And so this Myriad X was designed to be all these things. It has it's embeddable. It's a little embedded system. It handles high resolution, high frame rate you'd need. It has depth perception hardware built in. It's got greater than 30 frames per second AI with object detection and semantic segmentation. And then it's got the computer vision to tie it all together on an embedded system. So it actually was a lot faster and more performant than those multiple MacBooks in 2017. And gave you the depth of vision and handled multiple image sensors, 12 megapixel image sensors and 1 megapixel depth. So it was exactly what we needed, but there was no development kit. And so we built the development kit and we built a series of products around that called the Opencv Ai Kit. So here's one of them. And we were in this space where for months, we were just this is the chip. When's someone going to make something useful so we can use the chip, right? We want to use the chip. And so we were just scouring the internet, seeing what we could find, talking to everyone. At one point, I heard there was someone close to me, a 2-hour drive away, that knew something about it. And I instantly drove there and waited in their lobby, right? We really wanted this to exist. Because it would be so useful for us. We absolutely needed it, and we thought it'd be so useful for the world. And nothing existed, and we found that no one had any plans to make anything exist. So we either needed to just give up, which I tend not to do, or build the development kit. So we did that, and while you're doing that, when you're why isn't anyone making this, and no, everyone's refusing to make it, and we're spending months trying to figure out who's going to make it, and you decide to make it, there's this weird time where you're well, are we just doing something super dumb, or are we really on to something? And so we launched a Kickstarter, and that was the first time we really kind of got that answered. That people were yeah, we need this too, right? Why isn't this a thing? This chip would be so perfect. So launched the Kickstarter, and that validated that folks wanted to be able to have an embedded system that had all these capabilities and did want to be able to use this chip, which was the only chip in the world that so far that could do this. The team, the Movidius team and Intel team were way ahead of their time. And the guy who started this chipset, also saw this in the early 2000s or late 90s, that this was the thing that was coming, and had been working his whole career to make this. Myriad X was the culmination of his career in that regard. And so he was, of course, stoked to see that someone actually made it so folks could use it, besides billion and trillion dollar companies who were using the chip beforehand. So we launched the Kickstarter, and for this type of device, all the categories that it fit into, it broke all the records. So for any printed circuit board, it broke the record. For an AI project, it broke the record. CV project, it broke the record. Depth sensing project, it broke the record barely. Occipital, who I mentioned, had the record previously, and they raised 1.2 million in 2012, and we raised 1.3 million. So technically, with inflation, they probably still hold the record. So we did that, validated that people wanted it. So then the question is how do we actually access this? How do people take advantage of it? We really wanted it. And so we built what we wanted to find on the internet, right? Which is we didn't want to have to talk to some sales guy. We didn't want to have to put $100,000 or $500,000 or $20 million down just to prototype something. And most importantly, we wanted to be able to customize things, because when you're embedding something, you don't necessarily, maybe you want to buy one of these, maybe you want a little thing, and this happens to fit. This is our Oak D Lite. But there's a lot of cases, in our case specifically, like we wanted to build something with it. We didn't want to buy a finished product. We wanted to build something with it, and specifically this smart bike light on the right. So we made it open source, MIT licensed hardware, software, and AI training, so that anyone from a student, we've had high school students build custom hardware around this, could go build their embedded system. And so now it's this whole ecosystem of that. So these are all, everything you see here is open source. And the way, which begs the question immediately, how do we monetize? So we do all these open source designs, and then we have a system on module on there. So when you go to build something, we're just then a component on the design. So like you're buying a inductor from Murata, and you're buying a TRX-COM Ethernet or what have you, and then you're buying a Luxonis system on module. But we try to keep that as small as possible, and then folks can customize and integrate into tiny things easily. It's open source software as well. There's all sorts of applications out there that you can use. Open source AI training, and then also, like, one of the things that we're most excited about is how is it actually like open source? How do you integrate it? So it's open source at the software level. So you can integrate it with a Raspberry Pi or something that runs Linux or Mac OS or Windows or some OS we've never heard of. But it's also open source at the embedded level, at the microcontroller level. So one of the products, they all use the system on module, but this one has an ESP32 on it, on which you can run MicroPython. You can run other drone control algorithms, stuff like that on a pure embedded system. And then to the what, like I talked about, wanting it to be embedded, performant, spatial, with artificial intelligence and computer vision. This is our OAK-D model, also open source. And then, as I mentioned, the system on modules. These are what allow you to integrate this into what you want and customize any of this hardware that I showed here. And we have standard models. The reason for these is, some folks do just want to put these directly on a drone, right? Like you don't want to customize it. You just want it to fly. So, here's Oak One. You can think of this as, here's the existing solution. You buy a camera, you buy an AI processor, a Pi, and then maybe some controllers. You tie it all together. This combines the camera and the AI processor into one device. And we have the embedded version that I showed you that then also has a microcontroller built in. And then OAK-D is the 4K camera, stereo depth, and the AI processor, all those building blocks that I talked about into a single device. And then, probably more interestingly than all of those are super interesting for if you already have some Linux system on your micro drone, for example. But some of these drones, you don't want a Linux system, right? Like that adds weight and cost and power. And so we have this Iot Series, which is all of that. It's all of the processing that I talked about with an onboard ESP32, which then can be used to run embedded code. So folks have run MicroROS on it, for example. And on all of these, then it's OpenVINO compatible. So you do object detection, face, vehicle detection, pedestrian, text detection, and a bunch of stuff that we can't even think of. And the most important for drone applications, and really all of this is like the crux of everything, is you can run AI, so you know what objects are. And so this little GIF shows it's detecting me. This is colorized depth, and then it's detecting the chair, so you know where objects are. And then you can also use that point cloud information if you want, or run a class agnostic object detector, which can run on there, which allows you to detect objects even if you don't know what they are, right? Like there's some object that's in front of your drone, you have no idea what it is. You can still use an AI model to detect, hey, that's an object and it's in this position, which can be really useful for not having to parse point cloud data, because parsing point cloud data to detect there is an object can be painful, because you have to think of like, how do I classify something as an object and avoid it? There are class agnostic object detectors that you can use. And so in the embedded instance where you don't have a host processor to do logic like that, you can run one of those, combine it with depth information, and do obstacle avoidance or tracking. Pose as well. There's some cool examples where you can do like hand tracking, you can do person detection, then you can zoom in, then do pose to find like a wrist, choose which wrist you want to talk to, and then you can find palm, run a palm detector, And then you can do like sign language and control your drone in 3D space. So there's some examples online that we can talk about in Q&A. Semantic segmentation's really nice as well. You can do semantic depth, which is really nice for navigation as well. And there are all sorts of possibilities here. So you have 3 cameras, a pipeline builder that allows you to run arbitrary AI and depth processing. And so you can do things that we didn't even think of. Like we have customers who've run depth between the color camera and the grayscale, customers that run AI models in parallel. So you can detect the position of objects that standard disparity depth falls apart on. Like imagine a bunch of like mirrors in a field, right? Or like you've got mirrors hanging. Disparity depth's going to fall apart on a mirror because it's going to see the reflection and think that thing's, maybe the reflection's 50 meters away, and then your drone's going to fly straight into the mirror. When you run an AI model in parallel, it can still know the location of a shiny thing, which disparity depth can't. And so this is an example of stereo neural inference where you can see I'm actually in different positions, and then it's doing facial landmarks of my eyes, nose, and like edges of my mouth and stuff. Here's an overview of the features. So, running AI, getting location of things in 3D space, tracking those things. So I'll have a demo on a drone later about that, tracking in 3D. One of the things that we are super excited about and is you can encode directly onboard the camera in parallel to all these things. And that's super useful for when you actually go to deploy and you want to know what the heck happened, right? You don't have to record, raw video. So it takes it from raw video at 4K is like 800 megabytes a second, and encoded at H.265 is 3 megabytes a second, which is, you can even write to like a pi 0 really easily. And you can do lossless zooming, which is used a lot for when I was talking about defining a person and then finding like where their hand is and then doing hand pose. And a whole slew of other things like in JPEG. So then, what is this actually made of? So we're just simplifiers, as in my bio, right? I'm a huge believer in innovation, which is the steam engine was invented by a technician in a basement, right? Not a guy who worked at a billion-dollar company or a market cap leading company or anything like that. He was a technician in a basement. And the reason he was able to invent the steam engine is he had these easy to use tools and he was able to combine them in interesting ways. So the Myriad X is the underpinning of all of this. We just simplify it and we make it so someone who's a technician in a basement can go do something really cool, right? To make it easy. So, it has 4 trillion operations per second. It has these vector processors that allow you to run all sorts of different computer vision really fast. It's got these dedicated vision accelerators. And that was, no pun intended, the vision of this chip is, if you have a general compute platform like a MacBook, you can do all sorts of things, but it's not super efficient. So, and in a lot of these vision situations and perception situations, you already know all those tasks that you're going to do. So what if you just put those in hardware, like disparity depth in hardware, depth sensing as a hardware block, edge filtering as a hardware block, like optical flow and motion estimation as a hardware block, feature tracking and orientation as a hardware block. So it has those vision accelerators. And then it's got this crazy memory bandwidth to tie those all together. And then of course the neural compute engines give 1.4 tops of AI processing. And then on these models, which again are open source, so you can actually use different image sensors. There's a 12 megapixel. We found that was extremely useful so that you could just punch in, AI detects one thing, then you pull a high resolution out of that, it detects that, pull a high resolution out of that. And, 30 feet away, you're still like reading sign language off a hand. And then global shutter grayscale, so you can get high resolution depth. There are options for this, and we have open source reference design for all of these. So this is one of the standard, it's 1 megapixel depth. This smaller, lighter version is just 300,000 depth points. And then we have a higher resolution, which is 2.3 megapixel depth. Really easy to get up and going. So we have installers. You can just do, apt-get install on Ubuntu. The Windows installer is super easy. And then maybe more importantly, there's this whole community that we're developing. This all goes back to like the thing that we wished existed so we could develop our product easily and quickly. So we decided to take that upon ourselves. And then, finally, like where is this used? So tiny aerial and subsea things are a big one. Obviously, for this conference, that's super relevant. But generally, just tiny things where you want an embedded system, but you want it to have all these like human-like perceptions. So spatial AI and CV all together. E-scooters, micromobility. That one's actually kind of counterintuitive. One of them is what we originally did or wanted to solve, which is keeping people who ride bikes safe. But there's also flipping that on its head, which is people who ride e-scooters in downtown cities. Most of them are respectful, but there's always that jerk who like buzzes through people going really fast and unsafe and goes around blind corners. So you can have this installed in an e-scooter and know where people are and just automatically slow the e-scooter down. Visual assistance is really cool. This is human-like perception on a tiny device. So if you have visual impairments or you're outright blind, this can be a huge help because it can tell you where things are, is the vehicle on your trajectory or you're about to walk across a crosswalk and so forth. There's some really cool bleeding edge research going on there. Cargo, transportation, autonomy, all sorts of, how full are things, what's in there, is it completely empty? Sports monitoring, this has relevance with drone too, because you can punch in quite a bit. You can zoom in. Smart agriculture, all sorts of safety systems. In agriculture, you'd imagine, you know what things are and where they are. Picking strawberries, for example. Safety systems is the hand about to go into a wood chipper. Security, one of the applications is actually doing gun detection. And you can do it privacy first because everything's processed on the embedded system and tells you where a gun is. So you can just literally have a map of like, there's a shooter, which is a problem for potentially unique to the United States. And then microsatellite sensors, because you can do everything on a little embedded system. So then micro drones, we'll focus on that. Maybe drone isn't the right term, but let's see if this will actually play. Okay, cool, it is. So here's an Oak-D. This is obviously a bit of a bigger drone that was prototyping on. But the IoT, for example, is really small. The Oak-D light's really small. And so this shows running depth perception and a custom object detector trained for drone landing. So you can see there, it's finding the X, Y, and Z position, and it's actually guiding the whole drone. And then I'm going to see, excuse me for a second, turn the sound off on this. I'm sure you guys are very used to the sound of drones. So it's finding the target and then, auto landing based on that. So it's using the depth perception and AI. And the next thing that is being worked on this is doing all of this on an IoT version. So you don't even need a host computer, except for if you just wanted to visualize. So that's one example, precision landing. And then another, we've been responding to the drone community. When we first made this, we actually didn't think the drone community would want it. We see so much, from so many big drone companies, and one of the few companies that actually got access to the Myriad 2, which was the precursor to the Myriad X. It didn't have nearly as much AI capability, didn't have a depth engine, was DJI. And so we figured, well, are we really going to add value? Like, it seems like drone folks are covered, but actually there's a huge response because the ecosystem is customizable, so you can make what you want. And so one of the somewhat recent tests actually was we had an autofocus module in there because there's a lot of locations where you'd want to autofocus. So the default hardware was autofocus. So you can see on the right here is autofocus. And depending on how many vibrational modes and the amplitude of the vibrational modes you have on the drone, it can really mess with autofocus because the autofocus is it's electromagnetic controlled. It's a free moving lens, and the electromagnetics hold it like a speaker is moved. And so Rishab there at ArduPilot sent us this back, and we're like, well, that looks terrible. And so we worked with ArduCam, who's extremely responsive, and we love those guys. And they made a fixed focus version of our color module really quickly. We sent it back out to Rishab, and he was like, oh yeah, this is a million times better. So now we're offering everything in fixed focus variants as well. So everything can be ordered. And actually, he got us this information just in time for a Kickstarter, so that we worked with ArduCam, and it turned out about 70% of folks who ordered our Oak-D Lite, which there are 11,000 ordered in those 31 days, actually wanted fixed focus because they were putting them on drones or other heavy machinery, or drones aren't heavy machinery, but other things that vibrate like heavy machinery does, and lawnmowers and so forth. So this is an example, and you can see how it's just, you know, night and day different. Obviously, the 12 megapixel camera is still rolling shutter, so you can see a bit of like blurriness as an effect, but you know, it's still a ton better, and you can see the object tracker in 3D position a lot better. When this demo was run, this was actually debugged on our Discord. We have a Discord where there's a large community of folks who can communicate and prototype and debug. The threshold for distance was set wrong, so it was not allowing distance measurements above, I think, like 4 meters or something. So that's why the distance measurement is wrong on the bounding box on these, but you can see it's way better. So yeah, that's the IoT version actually is on the top there. Let me pause this, excuse me again. The IoT is on the top there, and that just happened to have an autofocus and then the fixed focus, but both are orderable with fixed focus. And this is Rishab, you know, his next objective that I wanted to present. This is, you can see it's very recent. That was 2 days ago. Someone was asking him, you know, why are you doing your next approach? And, you know, he says the IoT version is really interesting because it's the first time, you know, such interesting applications without a companion computer, which is our, you know, one of our core objectives, right? Robotics is a big one. UAVs, drones we view as, you know, flying robots. Right? That's fundamentally what they are. And embedded robotics is our core focus. And so that's what he's going after. That's what he's building in RGPilot. And on the right there, you can see one of the Opencv IoTs, where then that could be literally the whole thing on the drone that also just straight up controls the drone, which goes back to research in this conference, which is super exciting. And then on the left, you can see progressions. So all of these are actually buildable, especially since it's open source, in an IoT version. So it could be standalone. You just have IO that goes to your motor controllers, and it just flies your drone. So if you have some application, and say you train a neural network, custom neural network, you can just fly your drone directly, nothing else involved, which is super cool. And then to cover other applications of visual assistance, for example, here are some prototypes that are made. It's showing, you know, the crosswalk is ready to go. Is there a car in your trajectory? Those sorts of things. Precision agriculture, which also, you know, relates back to drones, because you can have the drone guided based on like what it's seeing in a field, right? Instead of flying the whole field, it can, you know, spend more time focusing on where there are issues. Health and safety, knowing where people are and where their joints are and so forth. And then, you know, this is a system we want to allow folks to just get up and going, where you don't have to do a bunch of work. So you can just buy this stuff online. There's Amazon Prime. Unfortunately, we don't have Amazon Prime in Mexico yet, but we're working on it. But I think you can still go on Amazon and they'll just ship it to you, but it's just not as convenient as if it was Prime native to Mexico. But soon Mexico and Canada are the next two. But then it's also open source. On the right here, you know, you can look at designs, you know, folks who design hardware or hack hardware can then, you know, go build your own or modify it or what have you, with the purpose being, you know, we wanted this, right? Like we wanted this to exist. We wanted it to be easy. So we tried to make it as open source as possible, so that folks can go solve their problem, you know, without being encumbered with talking to some sales guy and him trying to pitch you on, you know, $100,000 deposit on a license or something like that. And then on the left here, so we are still in pre-order stage for this Opencv Light, and actually on our campaign, you can see it's on a drone. This is one of the, you know, better products for going on a drone because, you know, since put a sense of scale, I do have a very large head, so it's kind of like cheating, but it's pretty small, right? And so that's one of the, we found out in the Kickstarter, one of the core applications, by the fact that in our survey, most people, we asked folks, do you want fixed focused or autofocused? And the number one response was fixed focused, using it on a drone. And so this is still in pre-order. Apparently we have 8,415 people as of when I screenshotted this. And all the others are readily available. Although we've been seeing a lot more sales recently, so stuff's been stocking out, but most of it is findable if you're just willing to go hunt a little right now. And And I think that's it. So here's me walking at one again. I always like to give more time for questions in case I missed. So I figured now would be a good time to open it up for any and all questions.
Great, thank you, Brandon. Very nice talk, and it's quite interesting. I like this video of the precision landing. We have done a couple of papers on that, and we have used the standard camera, you know, the one that we have with the drone, and then we did it on board as well using the Intel Compute stick. But it was slow. We have to say that, especially if we wanted to run CNN, a convolutional neural network, it ran at maybe 10 hertz, you know, like 10 frames per second. And then when we got this sensor and we began testing it, it was quite impressive because we could achieve from 30 to 40 hertz. So perhaps in that sense, what is the fastest network that you have been able to run on the sensor, if you remember?
Yeah. So you can have the fastest frame rate that Opencv can currently do is 118 frames per second. And there are definitely networks that will run faster than that. So you can do 118 frames per second currently on Opencv. In the way like the nature of research is right now is, I was actually just on this Edge AI Summit panel where we were talking about this, and there's only so much time, but fortunately we actually have time to talk about it here, where, you know, that machine learning researchers tend to operate in infinite resource land. Like they're training on the cloud, you know, they've got just almost infinite resources. And then folks who go build things, especially at the edge on a drone, are always operating in limited resource land, right? And then the folks who are on infinite resource land often are incentivized to use a lot of resources, because in that land, when you produce a research paper, the way you get attention is by being best in the world at accuracy generally. And it's kind of hard to even quantize like being faster, because like you can just be faster by getting a bigger number of infinite resources, right? And so you'll end up with these super heavy networks. And then you go to like port those to some embedded system, and you can like tune and make them better and so forth. But for the most part, a lot of the things, even the examples that we have available for the platform, are not yet anywhere close to like what you could theoretically do with the platform. If you convince one of those guys, and we've convinced one of those guys to leave infinite resource land and live in finite resource land. His name's Mattia, and he just joined and joined our company. And, you know, over the past 2 months he's been here, he's, you know, gotten probably 100-fold the number of models running on our device than we had in the past like 2 years. And so I think, you know, soon, probably like 2022, you'll start to see models that can run at you know, frame rate limited on the device. So, you know, 100 frames per second. And then Opencv Lite are lower resolution grayscale cameras, and they can run at 200 frames a second. And so then it's this game of, you know, the standard models will run at like 30 or maybe 40, like you mentioned. And then as you start to bring this research, because it's kind of a newer field of like, you know, limited resource, high frame rate, you know, machine learning training and architecting and stuff. And there are these like PicoDet and stuff like those. We haven't gotten those running to my knowledge. Maybe he did, and I just didn't notice yet. But those are very likely to be able to run at sensor frame rate, but we're just not there yet. So yeah, 40-ish, 30-ish, depending on the model. Semantic segmentation, we can do 30, but all of those, there's a lot of room to bring in, you know, it really optimized models. So yeah, you know, hopefully we'll have, you know, object detectors that could run at 200 frames a second. And so then we can already get depth on Opencv Lite at 200 frames a second. That's this little guy. And so then theoretically, if, you know, everything aligns, you'd be able to have depth at 200 frames a second and object detectors at 200 frames a second, which would be really cool.
Great, thank you. And yeah, one of the things that in my lab we wanted to use this sensor for was for visual SLAM, you know, simultaneous localization and mapping. And I mean, not only talking about using neural networks, but then exploiting the fact that we have depth, like almost for free. It's like a depth camera. But then on the top of that, you also have the color camera. So we are exploring how to combine visual SLAM and at the same time try to detect like semantic objects or do semantic segmentation with the color camera and then enhance your map with that. So because the idea is that if the sensor can do that, like the segmentation and the depth, and we just use it for rapid SLAM mapping, then not only for drones, like for robots in general, robots that have to navigate in a space. So what are your thoughts on that? Like, what experience have you got with this type of applications?
Yeah, I think I've seen some of your work on that, which is awesome. And yeah, I think it's a fantastic use of the platform. In fact, one of our engineers who joined, he applied to the very first Opencv AI competition, which was in 2020. Yeah. And his submission, which was amazing, was, he wanted to do SLAM, which was like AI object detection or semantic segmentation, augmented SLAM. And on the interview with him, I was like, yeah, like we should do that, but you're going to have to do horrible tasks first, right? Like our factory calibration and all those things. And so far I feel bad. And we just had a conversation about it. He's been very much so on like, making it so when we make 11,000 of these, they actually show up properly calibrated. But it is something that we're extremely interested in doing and wanting to, get a little bit off of like this horrible tasks as I describe them, to doing that. So one of the aspects of that is actually outputting, doing VIO directly on the camera, which we want to do, and then let's see, VIO, and then exploring just like what are the limits of doing that, and like you mentioned, having AI on board helps you to do loop closure at lower cost. It helps you to like reorient, because you're like, okay, well, I saw that coffee cup, right? And like I saw that coffee cup in its pose, or I picked up these specific features, and there's a whole ton of interesting possibilities there, because maybe a coffee cup isn't the best way to reorient and loop close, but there are common objects, say in your use case, that are right, like where you can learn, okay, well, these things have big baselines, and I don't know what they would be, but like big baselines in this situation, and you can find features on them easily. And so once you've done that, you can orient and distance very well, and you can full 3-dimensionally loop close. So yeah, I think it's a huge opportunity for the platform to allow that, and I think it's extremely useful in robotics and UAVs, pretty much anything that has to navigate in the physical world. So far, our platform is kind of just given some of the basis functions for that, but we haven't gotten into it itself, although we really want to, like you mentioned, depth, and then we have algorithmic feature tracking, which helps, but like AI based feature extraction and then labeling would be extremely useful. And so that's another part that would be extremely useful for generating a great SLAM. Is it's not just, okay, there's some features and we don't know if they're right or wrong, or when we lose tracking or not, but like that is this feature, we know what it is, and we can hold on to it, and we can re-identify it even when we re-enter the frame, right? So yeah, I'm super excited about that stuff, and we're kind of chomping at the bit to actually be able to do it. But we know, our customers of ours and folks who are building off the platform are doing it. So some of those, there's very initial attempts at it, like open source, and then we know there are customers who are building closed source things, and we're excited that they're using our platform to do it. But there's part of you that's like, I wish that was open source. So yeah.
Great, thank you. We have a question from the audience, so let me read it to you. So this is a question from Murat Bronze. I hope I pronounced it well. He says, I was wondering if Brandon can make a fast comparison with Gilles or Gilles. Do you know that device?
Yeah, Gilles. So it's, all this stuff is so, multinational, right? I was on the call recently, and someone mentioned, it was like, oh, all that was made in Russia. And I was like, yeah, I mean, when we're literally riding and at the front, all of us, whether it's folks who've been studying this for a long time or folks who are brand new to it, the we're at the forefront of human capability. Like this is a lot of like the fruits of the labor of human capability, and it's constantly moving forward. Yeah, Jevois is awesome. I have one. Our niche is having AI, which is what Jevois does. AI, Jevois and Opencv, for example. So our thing is like 5 things, right? So it's embedded, embedded system, like we talked about, as you all know, performant, which falls into multiple things. So multi-sensor is probably one of the most important. High resolution and high frame rate. High frame rate's a really relative term, but to put numbers behind everything, multi-sensor, so like 3 or 4 cameras on a device. Most of our stuff are 3 cameras. We have customers that are doing 4 cameras, 4 image sensors. The performant aspect is in high resolution. So this is 13 megapixel plus 300,000 depth points. We have other systems where they're doing 4 12 megapixel cameras on the same platform, or 4 2.3 megapixel global shutter. So that's the performant aspect. And then high-ish frames per second, right? 200 frames per second on OAK light. So we're talking about 5 things: embedded, performant, spatial is another big one. So the only reason people really use our stuff is if they hit 4 out of the 5 of these. If they hit all 5, they're like, yeah, I super like that thing. So spatial sensing, disparity depth is all the products that we have right now are disparity depth based, which is the same as human perception is disparity depth based. AI, so onboard AI acceleration, and then onboard CV acceleration to tie it all together. So if you look at like Jevois, it's very similar, right? But it's embedded, AI, and CV, right? But Jevois doesn't support multi-image sensor, right? Like you just buy, it's got a single camera, right? And so we saw Jevois and we're like, that's great. But for our problem in solving the bike or like the distracted driver problem, like we needed depth information. You needed to know how far away the car was. And someone would argue, well, why don't you just do what Tesla does? Like they use a single camera and they extract depth, right? From a single camera. And that's a viable solution, and it's a trade space. But the trade is if you have a ton of computation available and a lot of power, and you don't want 2 bumps on your Tesla door, you just want 1, a single camera is great. But the trade is like a depth estimator. So out of those, like that's missing on Jevois, that there's no depth. A depth estimator that's going to do a great job in real time takes maybe 25 trillion operations per second, right? And so our whole platform is 4 trillion operations per second. And so whereas doing depth algorithmically takes like 0.01 trillion operations per second if you have 2 cameras. So when you look at Jevois, they're embedded, AI and CV, missing multi-image sensor. That's just not their focus, right? Like we're different than that. And then they're they don't have depth information. And so that's really why folks would choose us. And then Opencv is the same thing. So embedded, AI and CV, right? They don't have multi-image sensor. They don't have super high resolution or high frame rate stuff, and they don't have depth sensing. So that's largely the difference. Those are great platforms. If you find yourself needing embedded AI and CV, Jevois is a great choice. Opencv is a great choice. I don't know the Jevois founder, but I think it's a great product. I know the Opencv founder. His product's great as well. And then if you find yourself needing 4 of the 5 of embedded, performant, spatial, AI, and CV, then we're a platform for you. And I think all of these 3 platforms are open source. I think Jevois is, we are, and Opencv is as well. Generally, if people need 3, they use Jevois or Opencv. If they need 4, they'll typically use us. If they use 5, then they send us thank you letters, if that makes sense.
Yeah, it does. And actually he says, perfect, thank you very much. And now that we are talking about comparing against other cameras or sensors, in the last years, maybe 5 years, there is this camera that has become very popular in the robotics community, the event camera.
Oh, yeah.
So I was wondering, what do you think of that device, and how does it compare to what you are offering?
Yeah, so we want to get a hold of like an event camera image sensor so badly. So if you guys like know how for us to like buy one and put it in the platform, we'll like release an open source design around it and we'll get it integrated. So event cameras are so incredibly useful. And we found some, RGCam has found some for us. But the ones that we found that we could actually purchase are relatively low frame rate, and their intention of these because there's a spectra of event-based cameras. The ones we want are the ones that their like effective frame rate are like 5,000 hertz. Because if you get those, and I know those are commercially available, you can just do insane like nutso level good job of SLAM. So all the things we were talking about, we have an event-based camera. We put that, slap that in, and that's the fourth image sensor out of that performant thing, right? So you have depth information at 200 frames a second. You've got effectively motion overlaid at the depth, interpolate that's actually in between all the depth frames at 5,000 frames a second. Like that's insane. Like your SLAM will be so accurate. And when things are vibrating or whatever, like it'll understand all of that. So the ones that we've been able to get access to so far are like 30 frames per second, which actually doesn't buy you anything in our case, because our cameras are already 200 frames a second and you can do differencing on them. But we were like super excited and desperately wanting to buy it. And then we did the analysis and we're like, that doesn't actually get us something. So we for sure want to do it. Now it begs the question, what are the 30 frames per second event cameras? What are those for? Those are great for privacy applications. So the ones that we've been able to find are privacy, where they literally just want a security camera that you can put in like a hospital room, and that has applications. So we may still build something off of it, but it's less relevant to drones, right? It's less relevant to SLAM. So if anyone on the audience knows of those that we could buy, we've seen those. Like I think Samsung for a while was producing a sensor that had those rates for event cameras. Anything 200 frames per second faster as an event camera, we'd be super interested in, because it's so helpful in SLAM. And that's the first big use case that I see for it. For the high frame rate, low frame rate is privacy. I think there's a lot of discovery that can exist on that. And when you look at it from like a biologically inspired perspective, I like to think back in that direction, because out of billions of years of evolution, a lot of things have been tried. In our eyes have event cameras built into them. So when we think about what our mission is to embed a lot of this into the sensor effectively, our eyes do a lot of that. We have edge filtering in our eyes. There's some research, I wouldn't be able to find it because it was from like 2 decades ago, that show they can actually show you what the world would look like to you if you didn't have edge filtering applied. Like we actually have very aggressive edge filtering applied in our eyes, and we're just used to seeing the world that way, because that's the only way we've seen the world. And you can unapply it, and there's amplification and so forth. But then there's also like event camera types of things that's built into our eye as well. That's how we can pick up things in our peripheral vision. So I think it's a key building block that we've kind of been missing. So I'm super excited about event cameras, and then just chomping at the bit to figure out, how do we get access to one, and how do we continue our mission, which is to make this stuff easy for folks to use, which the first aspect of that will be how do we find one? How do we actually find one?
Great, thank you, Brandon. Yeah, it would be very interesting. So there's another question from the audience. So what is needed to get the cost of event cameras down, in your view? How can academia participate?
Yeah, unfortunately, I have no idea. I don't know the architecture well enough. In terms of, so there's like 2 aspects of getting the cost down. One is like literally the cost of producing the thing, and I have not the foggiest. I have no idea. Then the second aspect is if someone figures out how to make a relatively low cost event camera image sensor, we can do the same thing that we've already done, which is like, the Myriad and all these technologies were in the hands of people with tons of money to be able to do these things. And they were the only ones that, had access, whether it was just literally, to pay a bunch of money, or it was too complex to use, or, it required too much specialization. We can help in that cost standpoint by just getting it out to folks, but I don't know enough about event cameras or just camera production, like the image sensor production in general, to provide any answer there, unfortunately. Sorry.
Okay, yeah, I'm the same. I wanted to ask you as well about this other camera. I don't know if you are aware of that. There is this camera built in Manchester University. It is called the SCAMP sensor. Does it ring a bell to you? So the idea is that each pixel is a processor. It has a small processor.
Okay.
So they're going to the other side, opposite to what the event camera wants to do, because the event camera is a sensor for very basic detection of motion, right? Like if a pixel changes in intensity, then it triggers something. So then if something moves in the frame, it will spike these pixels, only those pixels, and that's it. And that's why it generates loads of events. This other group argues that, yeah, that's something that maybe the AI does, but that is still quite low level, because then we have to reinterpret all that amount of data. So what these people are saying is that it would be better to process each pixel, like exactly what you said, right? Like if we want to apply filters, we do it directly on the pixels.
Yeah.
So it's a totally different approach. It's not yet commercially available, as far as I know. They are still in terms of prototyping, but they have shown things like running neural networks with these small processors for each pixel. They have used it for autonomous drone racing. So yeah, maybe I will send you the link. I know the professor who is responsible for the project. Piotr Dudek, I think is his name. Well, I will send you the details. And they have collaborated with the University of Bristol, where I did my PhD. Okay. So with my former boss of the postdoc. So that's why I know them. But that is also another interesting approach. And I was wondering whether you have any ideas as well regarding this idea of having processors for pixels, or one pixel or group of pixels.
Yeah, I think it's a fascinating idea in like covering the trade space of like making new things like this that are, approaching human-like perception. I think one of the first things that's worth exploring is, how do humans do it and how do other species do it, right? And what you're discussing here, I think is in the eye, right? Like it's flexible and it's not a full brain, but there's a lot of processing in the eye. And so I think it's for sure a worthwhile path. And I think there could be a lot of interesting things. And then in addition to, exploring what, human perception has done, as we've seen in other technologies throughout history, like airplanes, for example, you observe what nature does, you take some interesting things from it, you observe what fish do, you take some interesting things with it, and then you build an airplane, right? It's not at all what a bird does, right? But with our set of technologies. And so I think not only is that worthwhile from like the biologically inspired, but I think there's a high probability out of that research that something that we don't do as humans, because it doesn't work well when you're made of carbon in transitioning to silicon, to discover new things that don't work on humans, but will work in technology that maybe are kind of like analogous, if you will, and extremely valuable. So yeah, I'm super interested in that research. I think there's a lot of fruit to be had getting this processing as close as possible to the image sensors.
Great, thank you, Brandon. Well, the last thing I would like to say, because people have asked something else, so I will take the opportunity to tell you this. The reason why I thought your talk would be very interesting to this community is because in these events, we don't only have a conference, we also have competitions. It's unfortunate that because of the pandemic, we didn't manage to run the competitions. We wanted to do it here in Mexico. It would be the first time that many people would come, but well, next time maybe. Yeah. But in the past, we have got competitions, and there are indoors and outdoors competitions. And there are several challenges where I think spatial AI is needed. So this calls for smart drones, intelligent drones. That's how I call it. So this conference offers a good mixture of aeronautics, like very nice designs of drones, and then this other side, which is like robotics for drones, for aerial robotics, because then we have missions where the drones have to enter a building. I remember one of the first competitions we attended in China. There was this small house built in a gym, and the drone had to enter the window, either the window or the door. And we used a SLAM just to follow waypoints. But the clever way would have been just to detect the window or the doors, and you enter. And there is another challenge, which is whether the door is open, right? So, and things like that, like counting people, or if you want to deliver a parcel, to do the precision delivery, you need to identify the spot. And if you run all of that on board, then this is the type of technology we need. In our project that we submitted to this Opencv AI competition, we did warehouse inspection. And that was the challenge of the IMAV 2019. warehouse inspection with drones. And we did it with our Intel stick computer, a conventional camera. But yeah, it was really, really hard. And then we got your sensor, and it became quite easy, just to implement everything. So anyway, that was the reason why I thought your talk would be very interesting to this community. And I thank you very much. I'm deeply honored to have you here, and I hope
thank you.
You also enjoyed the time.
Yeah. And then actually, I know we're literally on the last minute, but one thing I wanted to mention is, in the spirit of that competition, one thing that we've seen that would be extremely useful to the community now that we've built like a layer is synthetic training. So what we're working, really intensely on right now is combining Unity. Unity's working on this intensely as well, and we're getting a lot of the fruits of that, getting a virtual OAK-D and our whole line into Unity. So in that house example, like if you know the specs of the house, you can literally make it in Unity, get 2 million views of it, train your object detector or semantic segmenter, and refine a model, and then literally have trained models that have seen millions of views of that house, all with synthetic data. And you can augment the house to be different colors and different lighting and all sorts of stuff because it's all in simulation. And you have the 3 views and the depth information and so forth. And you can show up to a competition where you're just like armed to the teeth with specific models that understand every aspect of the house, right? And that's one of the things we're really excited about, like in the warehouse navigation and so forth. You can make these scenes so quickly, and having the capability to do SLAM and to record this data, make SLAM, you can literally go, fly a drone, record all the information, recreate that literal warehouse in Unity, right? And then you can augment it, change it, so that you can, synthesize all sorts of different permutations, so that it'll work in different warehouses, different competitions, and so forth. So that's the thing I forgot to mention in the presentation, is kind of what's next in a lot of the Unity-based simulation and synthetic training, synthetic testing, and everything with the platform. I think is going to be super valuable, and of course, we'll open source that all as well.
Yeah, of course. And just one more minute, because after you said that, of course, I was thinking of what people from MIT are doing with autonomous drone racing. So basically, they are building these arenas, the racetrack. I'm not sure if they use Unity, but well, they have AirSim, which is, I think, similar. So they are recreating these racetracks so that you can get access to loads of images. But then the other interesting thing is that maybe, for this problem is that how do you build the racetrack, right? You have to build the gates, and all of that becomes very expensive. So, but if you had a virtual racetrack, and then if you have the space, like let's say an open field with maybe Vicon cameras or even a SLAM, then you can work out, given the position of the camera, you can work out what the drone would be seeing according to this virtual space. So, and that's why actually once I asked to one of your colleagues, I think, or to you directly, I don't remember, by email, whether it would be possible to send images to the sensor. So rather than using the images from its cameras, just to bypass it and send other images, because then we could do that. Yeah, and
you can do that. And funnily enough, in 2017, like exactly what you described, I wanted to build that as a company, which was making virtual races, right? Like you use SLAM, you use onboard processing, and then all you have to do is an open area, that has some visual interest, which almost all outdoor areas have. And then you can make virtual courses that you can fly through in FPV, and literally have competitions that way, which I think would be really cool. And I think we're approaching the capability to do that now with probably the current generation. I think you could build something with that, but it would be work. And then we're also working on our next generation, the next generation of the Myriad X, which is just faster at everything. So I could very easily see that being a thing in 2022 using this, which would just be, so cool, right? Like you can have real life virtual racing effectively.
Definitely. Brandon, it has been a pleasure and a privilege to have you with us. Thank you. Thank you very much indeed. We will send you a virtual certificate of your participation. But
thank you.
Apart from that, thank you.